welcome everyone. I hope this sound is fine. Okay, so what did we do last time? Last time we just there was some sort of motivation. Why do we care? Just to remind you that last semester, in some sense, you can see it in a way that last semester we sort of did like the bare problem without like having any extra structure. So like studying manifolds without structures. It's not even true. We did some other stuff as well. But anyway, now we are kind of putting a metric on stuff. So we are doing an analog of Riemann and metric. And last time we essentially recalled the current authorities and the global classification for exact ones and local classification of the transitive ones. And okay, and so now today we will make the next step and talk about metrics. Maybe I was wondering, I wanted to give some references. Okay, I should. Maybe let me start next time with that. Quickly, but it's also today. Let's start with generalized metrics. Generalized metrics and half densities. So a lot of the geometry that we are going to discuss will originate in string theory. So just to give some pointers. So this thing is the stuff that is. So these two guys together, they are supposed to describe the bosonic massless field content of type 1 string theory, if you want. You don't need to know what that means. Well, we will get there anyway. We will see. You will see what this amounts to in terms of ordinary geometric quantities. Okay, so let me start directly with the definition. So a generalized metric on a given Courant algebra E of M is a symmetric vector bundle map and we call it curly G that goes from E to E. We find the property that it squares to 1. Okay, so now what is the meaning of these words? So symmetric, remember Courant algebra in particular has a bracket, a pairing, and an anchor map. So for most of what we will, actually for everything that we will do today, the bracket will not be that important. First, we will just play with the pairing here. And so when I say symmetric, I mean symmetric with respect to that pairing. So symmetric means that if I take the transpose, it's the same, which is the same condition as saying that if I form a bilinear form by putting G before calculating the inner product, then I want this to be symmetric. Okay. The vector bundle map simply means that it's vector bundle map covering the identity. So this means that it's really at every M, this GM is a map from the fiber to itself. Okay, so it's fiber-wise. And squaring to identity means squaring to identity. Okay? At this stage, it should not be obvious why it's a good idea to call this a metric, because metrics usually don't, there is not even a sense in which you can say the metric squares to identity. But you will see. And maybe actually right now. So let me state the lemma. Okay, not right now, in a moment. First, there is a lemma. It says that there is a one-to-one correspondence. So I want to rephrase this somewhat differently between Okay. Correspondence. Correspondence is such maps, generalized metrics, satisfying this thing and this equals to 1, and orthogonal decompositions. Of E into the sum of two subspaces, and okay. Actually, there is a third description. Okay, so probably I don't know, 1-to-1-to-1 correspondence or something. So, this one is just subbundles V plus inside E, such that the induced inner product on the subbundle is non-degenerate. Okay, even more concretely, this is kind of silly lemma. I mean, I could have just taken this without the lemma. But what are maps in this direction? Can you guess? Like for instance, how do I go between these two descriptions? Like let's say I'm here. I have a splitting. How do I get the subbundle V plus? So if I start with V plus minus, and I want to go here, what do I do?
Perfect.
Yeah, I just take one of them. I take V plus. I mean, out of this data, compare V plus V minus, take that. How do you go the other way if I start with V plus? How do I get an orthogonal decomposition? So I take V minus to be the orthogonal complement. Okay, so yeah, this is just like having an orthogonal decomposition. If you have an orthogonal decomposition, if you have one of the spaces, you can construct the other by taking the complement, then the orthogonal complement. And the only thing you need is that the inner product here is not degenerate. So this is what you need here. So this part is kind of easy. Here it's also easy. It's just you start with a G, and then you take V plus minus. Define this to be the plus minus 1 eigenbundles of G. Okay, so maybe I should let me I don't know, maybe I shouldn't need to call it a lemma. But okay, I already did, so let's go to lemma. Okay, so why is it a one-to-one correspondence, or like, okay, let me write the other way as well. So if I start with the orthogonal decomposition, so if I have V plus and V minus, then I can take G to be the reflection with respect to V plus. Or in other words, G on V plus minus becomes simply plus minus 1. Okay, so now how does the correspondence work on this stage? So if I have a map which is everything is pointwise here, you see that it doesn't really matter if I can just focus at a given point. And having a symmetric map in particular is always diagonalizable, and the eigenvalues of that needs to be plus minus 1, because this squares to 1. So you know that there is two subspaces, you know that they are orthogonal, that's another thing that you know from symmetric maps, and you know that together they give the whole space. So you get this, and the other direction, it's just, you can easily see that this thing, because it's plus minus 1 on these two subspaces, then plus minus 1 are both symmetric and square to the so, okay, I don't want to spend too much time on this, just to say that, okay, so there's various ways how you can rephrase this. It is often cool to think about the last thing. You just have a subbundle. And changing a generalized metric means you change a subbundle. Okay, so that's just a sort of algebraic thing. Now, okay, let's do some more geometric stuff. So first, recall this thing about exact Coulomb algebras. Recall that there was a one-to-one correspondence between exact current algebroids over M, some complete manifold, modulo isomorphisms, so isomorphisms covering the identity map of M, and the third cohomology of M. So if you remember, this was this Chevalier classification of exact current algebroids. This is part of what we did last semester. And the way you do that is that, like if you have an exact current algebroid, this exact current algebroid means that the associated sequence is exact. So there is an associated sequence and it is exact. And the way you can prove this classification was that you start by taking a isotropic splitting. Okay, this is the maybe not. So this is a separate picture. That I'm just briefly recalling what was happening before. So you started with an exact current algebra and you chose an isotropic splitting. So we showed that such a thing existed always. And once we did that, then we can identify the algebra with the sum of these two things, and the bracket will have some specific form in which there will be a 3 form appearing. And if you choose a different splitting, then it produces different 3 form which is cohomologous to the original one. So that's why the relevant part was with the cohomology. Okay, so this was just a brief recap. Now we want to set this in our framework of generalized metrics proposition. Again, another one-to-one correspondence. There is a one-to-one correspondence between exact current algebroids over some manifold M with a generalized metric such that it's positive definite. Okay, so by this I mean that this operator is positive definite. And up to again the same Isos covering identity, to be completely precise. The same stuff as above, but I am on top of that getting a generalized metric. And this is one-to-one with pairs GH, where G is a Riemannian metric and H is a particular closed reform. Okay, so difference is that here we have a cohomology class, here we have a specific representative and a specific Riemannian metric. Okay, is the statement clear? Yeah. So if you, this is another kind of contact point with string theory. In string theory, you study strings moving in some background, and this is kind of the data that you have. So last time I think we did sort of glimpse into that, but we only talked about the 2 form. So the proper interpretation of string theory is that you need to have a 3 form. Furthermore, it needs to be integral or something, but we don't care about it. Okay, so let's show this. This in particular should kind of point towards why we call generalized metric, because it generalizes the notion of a metric by adding another data to it. Okay, so how do we do this? So let's say starting with the current undergrad with exact current undergrad. We do the same thing as here. So we pick isotropic splitting. So we pick a map like this, and this thing inducing. Inducing an identification of the current algebraic with a concrete current algebraic. So with one of these we call it ECA-MH for some H. Okay, so in other words, if you remember what this was a specific current algebroid which looked like Tm plus T star m, pairing, anchor, and those are the obvious ones. And the 3-4 and the bracket here is the kind of the obvious one, the standard one. Plus there was a 3-form term. Alpha, y plus beta, and there was a term which looked like this. Okay, and if you remember that the classification business was actually showing first showing this, that there is a 3-form like this, and we also showed that if you choose any other different isotropic splitting, then you get same stuff with this thing differing by some exact 3-form. Okay, so suppose that we pick such an identification, so now let's forget about our general current algebra and let's already work with this identification, but let's keep in mind that this identification that we've chosen, and this 3-form, is not unique. We can change it, okay? But let's now work with T plus T star m. Okay. Is that clear? Okay. So now, since now we'll just work with this identification. Okay. So now, since we assume that G was positive, then if you think about what it means, for instance, using this, then it claims that this, then the inner product on B plus is positive definite, and the inner product induced on the B minus is negative definite. The current pair, I mean, the original one. Precisely because of this, that if you compose it with this G, which what does the G do? The G flips the sign if you are on B minus. So that's why if you want that that's positive, it means that this better be negative and this be positive. Does that make sense? Am I too fast or too? Okay, so far this is just like pretty much just a linear algebraic statement that I have if I have a operator which is such that this composition is positive definite, then it means that the eigenspaces are the induced inner product on the inner product on the eigenspaces is positive and negative definite. Okay, think about that. That's confusing. But what this implies in particular is that because what was the signature here? So this thing had signature n, n. So there were n positive eigenvalues and n negative eigenvalues. So looking here, it means that the conclusion I want to draw from all of this is that rank of V plus is the same as rank of Tm. So it's precisely, so such a generalized metric on extrapolant algebra precisely splits it into two orthogonal subbundles which have the same dimension, which is the dimension of Tm.
So this is like the
Oh, yeah.
It wasn't like this. So you are starting from assuming you have the G, the automorphism of the bundle, which is positive definite, and this is how it's defined. It wasn't.
No, V plus and V minus are defined to be the eigenvalues.
Oh,
Eigenvalues.
from here. Okay.
Yes.
Okay.
So they are the, yeah. So, okay, I mean, okay, should I comment more on the implication?
Maybe.
Okay, so if this is positive definite, it means that if I take, for instance, if I take, let's say, I take some element in E, which is non-zero, then positive definiteness means that this thing is positive. Now I can, in particular, look at, so, in particular, I can take, let's say, I can take X to be in V plus. Okay, I already have my G, so I have a splitting.
Mm-hmm.
So I take X, which is an eigen, which is in V plus, which means this is to say the G on X is X. It's in the plus eigen.
Yes, sure.
It's a plus eigenvector. Okay, so if I plug it in here, then so if I plug it in here, then because it's this, then I get that XX is bigger than 0.
Okay.
Right? So this is true. This I suppose this is true for all of them. This is equivalent to this thing with positive definite.
Mm-hmm.
Now, if I take this to be in particular living in V plus, then because Gx is x, then this just tells me this. So this holds for any x in V plus. So this implies that the pairing here is positive definite, which I denoted maybe rather sketchily by saying that it's bigger than 0.
Mm-hmm. Okay.
Okay, and if
I
I
was confused because I didn't realize that you're already assuming you have all this.
no, yeah, I kind of assume, yeah, sorry, I will be, from now on I will be interchangeably referring to generalized metric either as G or V plus.
Okay.
Sorry, yeah. But, okay, and the same for V minus.
Mm-hmm.
If you have here it's a plus minus, and then we have plus minus.
Okay, thanks.
Thanks, yeah, good. Please, okay, so anyway, the linear algebraic consequence of this is that these eigenvalues precisely split this thing into two bits of the same rank. Okay, so in other words, you can say like this: this is T, this is T star. Okay, I'm sitting at some given point. Let's say this is some given point. Now, what the generalized metric does is that it gives me an orthogonal splitting of this space into two subbundles. And they are orthogonal to each other. I don't know, is it denoted like this? The picture is a bit misleading because from the picture it also seems that the white things are orthogonal to each other, but they're not because they are Lagrangian. So probably better picture. But at least I mean V plus V minus are orthogonal. Please ask more questions. If they're confused, if it's possible that it's quite probable that I said something very confusing. So. Okay, well, you can still ask later. Okay, so better picture. Better picture would be something like this. I don't know, T star M, and then maybe, to draw purposeful this thing not orthogonal. And then And then, yeah, but it's still true that I have a B plus, B minus. This is maybe a better picture, but I don't know. Well, you know what I mean. But this thing doesn't emphasize the fact that they are orthogonal. They are not orthogonal. And white things. Anyway. Okay, but anyway, there is one thing that the reason I draw this diagram is, first of all, it's good to have graphs and diagrams. But the other thing to note is that that we also have the property.
So when you talk about orthogonal, you measure with respect to pairing or with respect to G and pairing?
Very good, very good. With respect to pairing.
Just with them.
Yeah, with respect to pairing. Yeah, so this is unfortunately, in the literature, people often do it with respect to this. Throughout the course, whenever I say that things are orthogonal, I always ever mean with respect to this thing. I never use this. I never use this as the inner product.
And why?
I don't know.
I would say the metric is the one that tells you.
Yes, and you would be right, but yeah, that's just the way I do it. Right.
And then on this thing, you drew Tn and T star as not orthogonal. That's because of the H.
No, they are just not orthogonal. They are Lagrangian, each of them. They are isotropic.
Okay.
They're like light cone directions.
Okay.
Yeah, I guess it's the same picture in like 2D Lorentzian metrics. Like you say like you have space and time, and you draw them like this, and they are orthogonal to each other. But then you also draw that they have light cones, and they are not orthogonal to each other. But on the picture they look like they are. But yeah, they're not because they are now. But yeah, there's just no way to get this.
So it's kind of being Lagrangian is exact opposite, no, of being kind of orthogonal.
Yes,
complements.
I guess so.
Because
Yes.
they are orthogonal to each other, but maximally non-orthogonal to.
Yes,
themselves.
yeah, it's exactly, it's exactly switched. Thank you. Yep. Yeah, this is the fate of working with inner products of like split signature. What can I do? Okay, so one other implication that we have is that we know that this is 0. So if I intersect, so I suggested we drew them like this, that this kind of doesn't intersect T star M. So now why is this true? Can anyone see why, based on the assumptions that we have, why is it true that there is only the 0 vector that sits both in B plus and T star M? So the hint is that you should think about the inner product. How does the inner product work? Like if I take any non-zero vector here, what is its inner product with itself?
0.
Well, on the other way. For this one is positive. B plus. But if I take something in T star M, then
Like in the intersection.
yeah, well, yes. I mean, it's both 0 and non-zero, so. Okay. Like, yes, so vectors here, okay, so all non-zero elements have positive norm, positive inner product with themselves. Okay, no, that's nice. Have almost all non-zero elements x have x, 0, while this thing is Lagrangian. So all elements x have x, 0. Okay, so the only way to have both satisfied is that x is 0. Okay, these are the two subspaces which behave maximally differently from each other. This is the one where it is like null. So all vectors are orthogonal to all other vectors in there, right? I mean, you remember how this inner product worked. It worked by pairing one forms with vectors. So in particular, each of those guys separate was isotropic.
And this is true for all 4 choices, not also B minus and T.
Yeah, it's also true for T. Or B minus, all four. Yes, but while I'm using this one, so the fact that together this and this imply that I can view V plus as a graph of some map. Graph of a linear map which goes from Tm and ends in T star. Okay, so let's call the linear map I know lambda. So what do I mean by graph? I mean that this is a collection of x plus lambda x. X runs over all things in Tm. Okay, this is the consequence. So if you want to have something that's a graph of some of a linear map, then first of all you need that this thing intersects trivially with this thing, because otherwise you have 2 points about the same point, which is not a graph. And second of all, you want that the dimension of this is the same as the dimension of this, otherwise it's not a graph. So you need these 2 conditions to ensure that. Okay, but now, okay, so what does it mean to have a graph? Or sorry, what does it mean to have a linear map? So such linear maps, it's like one-to-one to saying that I can, instead of talking about the map from here to here, I can put both of them on the same side, and I can say that this is the same as having an element E, which is a covariant tensor with 2 covariant tensor. So a section of T star M, tensor T star M. Okay, and then lambda x is simply E, where I insert x in the first level. X in the first level T. Okay? And then what I do is when I look at this, I realize that this has a symmetric and antisymmetric part. So then I can write this G plus B, where this is symmetric and this is antisymmetric. In fact, for reasons that, what are the reasons? Aha, okay. Sorry, just align this with my notes. I put the prime here, because this is not that edge. Sorry, so this is, so let me put a prime on all the edges. Yeah, right there, and here let me put the prime here. Just because I'm good. Sorry.
So all are primed, or there is some?
No, all the, yeah, because I want to distinguish them from this data that comes with it. Well, secretly G will be already the same, but we don't know that yet. Okay, so now what is the result? So the result was that we started the current with a generalized metric, and we make a choice. We made one choice, which was that we choose an isotropic splitting. That choice led to an identification with T plus T star, and it left, like this graph stuff, to a symmetric and antisymmetric curve. Now the question we can ask is like, so what does it? Okay, so in particular, so we got. Okay. So we got choosing. Choosing the splitting, isotropic splitting, isotropic splitting, we obtain a triple, G prime, B prime, and H prime.
So H and B are not yet related in
No.
any way?
No. Now, okay, now the only thing to address now is that what happens if we choose a different splitting? This was obviously a choice. So, okay, what if I do different splitting? Okay, so how does the different splitting work? This is the last part. So what does the different splitting do? Different splitting tells us this is our. We already have one splitting, which let us identify our current algebra with this. Now choosing the different splitting means that we now have a map, different splitting, which is a map tau from Tm to E. So if you look at its image, it will be, I don't know, something like this. This is image of tau. And the way this works is that now with this new splitting, we declare this is our new Tm. Okay? So all these things lives in a current algebroid, And by splitting, by choosing a splitting, we are saying how Tm sits inside E. So different splitting, so choosing a difference, choosing some splitting would simply result in something like this. Okay. Okay. Now, making again the same sort of manipulation again, because this is a splitting. It again transfers to this. It has the same rank as this. So again, this is a graph of some object. And if you remember, I think we did this in the first semester. The isotropy of this thing. This was an isotropic splitting. So isotropy implies that B is actually antisymmetric. Yes. So if you run through through the same kind of argument, it's a graph of some things, some two tensor, and then you need to check that all elements in there are orthogonal to all other elements, which is what our isotropy means. The condition for that is that it's closed. Sorry, it's not closed, antisymmetric. Okay? The moral difference splitting relates to the one which we already chose by a 2 form. And the last calculation to do is that, okay, now we just need to check what would this different new splitting, which is represented by a 2 form, what does it do to this data? How does it change it? And, well, there's not much that we can do to produce a new data using a 2 form. So let's check that. So that's this last thing. So remember that our B plus was the graph of some G prime B prime. So we had some B plus here. And we saw it as a graph from that's a graph of this, which is to say this thing, where I insert this thing in the first form. And what do I want to do now? Now I want to see this thing again, but now I want to, I take the same subbundle, but now I want to split it into the new T star, T prime, T to the new tangent bundle, and the new cotangent bundle, but the cotangent bundle is always the same, so this guy stays the same. You see it in there. Like, the thing we are changing by the splitting is Tm. In other words, I can write this. So, in terms of our new splitting, there will be some new symmetric form, new antisymmetric form. Okay, so and I want to deduce what this data is. Okay, so I just sorry, this is confusing. So you just have the one space, and you have this one subspace, and you are trying to decompose it with respect to two different decompositions. One of them is the original one; it gives you G prime and B prime. The other one is with respect to the new tangent bundle, which is this guy. So this one will be tau of y plus this. Sorry, full stop here. Good. Okay, now we just substitute and just like what is tau of y? It is graph, so it's y plus b of y. And now I just look at the two sets at this equality, and I can deduce that g has to be g. So g prime has to be g double prime, and b prime has to be b plus b double prime. Really? Okay. Yeah. Okay. So the moral of this painful algebraic calculation is that if I choose a difference splitting, so difference splitting parameterized by some by b gives a new triple, which is first of all the metric is the same. Okay, so okay, let's look at this first, but the important important thing is that this metric is the same as it was before. The 2 form will be, well, the original one where I guess we subtract b. And what is the new h? Double prime, so here I will just refer to the calculation we did last semester, which says that if you choose a splitting, if you choose a different splitting, then the 3 form that you get it here, in the bracket, it changes by d of b. You just have to remember the sign. So the sign here is, yeah, okay, I don't remember the sign here. What is the important? Okay, so this is plus minus d of b. One of the signs, I just don't remember which one. So, okay. So now we can conclude that in particular you see that there is precisely one splitting. If you start with the exact current algebroid and the generalized metric, there is precisely one splitting in which this second slot is empty, is 0. So there is precisely one splitting where you can eliminate this b double prime. And hence the data of a splitting, the data of a current algebra with generalized metric is the same as the first and the third thing if you choose the second one to be 0. That's why it's a 2 form, a metric, and a closed state form. Okay, so there's.
Okay, so that's why this B is not in the proposition.
Yes, exactly. Yes, yes. Okay, so let me say that again. So thus. It's one way to see the correspondence for a given exact current algebra. E is exact. I just shortened it to be E. Exact current algebra and generalized metric which is positive. There exists there exists a unique splitting, or in other words, a unique identification with T plus T star, such that B plus is the graph of a symmetric tensor. So G, graph of some G. And yes, so and this splitting results in a concrete freeform H. So this is how you get that. Now the last thing to close this, we need to check that this is a Riemann metric, and in particular non-degenerate. So far we know that it's a symmetric thing, but this is easy. So now, okay, if so let's say in this splitting, under this in this identification, we have identification. We take now, what do we call it? For any vector which is non-zero, we know, right? So any such vector, we can lift it to an element of V plus. So, okay, because V plus was a graph of this, so it was all x plus g x into m. And we know that this is V plus, and we know that V plus is positive definite. That's what we showed. So we know that this element, if I pair it with itself, it is positive. Okay? So here I'm using, here is the theorem, but I mean, we are assuming the big G is positive, which means V plus has a positive definite pairing. So whenever I take such a thing and I pair it with itself, it should be positive. But now, okay, now how do I actually calculate such pairings? In the formula that I raised, in exact current algebroid, I just pair vectors with covectors. So I pair covector with vector, so I get gxx, or I pair the covector with vector, which I get, again, gxx. So I get 2 times gxx. And I know that this is positive, hence G is a Riemannian metric. G is positive. Okay. That's the end. Okay. So the moral of the story is that there is a preferred splitting if you have a Courant algebra which is exact and you put a generalized metric on it, and you assume it's positive definite for now, then it gives you a preferred splitting, namely the splitting in which V plus is the graph of a symmetric form, and in particular, because it's a splitting, it bleeds in the bracket to a concrete tree form. So in this is how you get G and B. And H, sorry.
So, could you maybe comment on how this stuff works in that this is given module, the isomorphism covering the
yes, so the that bit was already.
Okay, I'm kind of confused that wouldn't the isomorphism like change the representative or because I don't really remember how it was done in the normal case.
Okay, let's think. So, yeah, okay. Well, okay. So, let me say the following. I think, okay, maybe the best way to answer your question is actually just to say, one observation that, I mean, the direct answer to your question is that if you change the identification, Anyway, let me say the following. I hope that clarifies it. So what did we say before? So the exact Brown algebroid plus this thing, modulo isos covering the identity, the same as G and a concrete tree form. So. Hmm?
Yeah, are you sure that like it's one-to-one correspondence with this modulo thing? Because I think it's one-to-one without the modulo thing. Because you're somehow fixing the splitting. So then you don't have the freedom on the left-hand side somehow. So it's like you have an exact ground algebra with ground metric, and you have a clear map that gives you the data G and H. And
Yes.
because when you act by like isomorphism on the left hand side, you also change like the Jonas metric to not be only like graph of G, right? It's then like graph of G plus B.
Yeah.
It's the action of the isomorphism.
Right. So.
So if you want
Okay. Sorry. Okay. Okay. Maybe what I really want is like an isomorphism of this pair. So I really want to have isomorphisms which preserve G, which would kind of, in particular, tell you that.
that it's just like
Well,
B is equal to 0.
Well, but
Like B transform is not transform somehow, right?
Yes, but I still, yeah. I mean, I know what you mean, but I wanted to be careful when, like, you know, like I take, you know, am I talking nonsense here? Like, if you take the standard Courant algebra and you take it, you know, take it again. Sorry, like twice. It's the same thing, but you know, you just have it twice. Then they are different, but they are isomorphic. So I want to model by that isomorphism. Maybe I'm, you know, it's like in, yeah. Does that make sense? Like, you know, like I still want to have some, because you can have like infinitely many standard Courant, infinitely many isomorph. What do I want? Yeah, I guess what I want is I want to have isomorphisms of the whole pair. So isomorphism is such that fine, such that phi G is G.
Sorry, but isn't it the point that the ECA, like that one with fixed H, that is a representative?
Okay, yeah.
So this
Okay,
means that if you fix that, then you don't need to model by it.
Yes, sorry, I got, yes, my old notation, my old notation has now caught up with me. I mean, I was, okay, so there was this one particular object that I called ECA,
Yeah, the one.
but here I just meant, yeah, sorry, here I just meant exact Courant algebra.
Okay.
Sorry,
Yeah.
maybe that was a really bad name to call that object before ECA. So, okay. Because, yeah, before I called ECA to be the specific one.
Yeah.
Yeah, I'm sorry about this. I think this confused myself as well. So maybe let me either write it like this or just not write it at all.
So, but it is true that if we instead like change this, if we fix the specific one, so the representative, and don't model by anything, that is one-to-one with the G and H, no cohomology, like closed.
If I don't want that?
If you don't
But
model,
if I
but you put a specific.
Yes, then that's true. Yes.
Right?
Yes.
Then it's one-to-one, not with a cohomology class, but
Yeah, with a
the
specific one, yes.
specific one. Okay.
Yes.
Because you're fixing the gauge by eliminating B. So
Yes.
you're also fixing
Yes.
the representative.
That's right.
So, okay. So you can start from that, I guess.
Yes, but I want it to be, I kind of want it to be more general, although it's really the same level of generality, I guess, because we know that every exact Courant algebra is really ECE, the ECA, sorry. Yes, I agree with you. Maybe I should have just said that, like, but I think this is also true. I'm just wanting out my, you know, I just take the. Sorry, this is becoming less of a lecture and more of a, like my own transferring my own confusion to a discussion fund. So let's say I have two algebra. You know, I have this algebra with a bracket and a pairing and a row, and I have a second such thing with the same bracket and same row, but I call this one E prime and I call this one E double prime. But they are obviously isomorphic. Yeah, but here I want to model it like that. I want to see them as the same for purposes of this pair because they both induce the same G and same H. So I'm just modeling out by like this silly identification. Okay, I'm sorry about this. Okay, I guess if yeah, I think it's probably more instructive and still true, sufficiently, appropriately expressed that this is true without the question. So, yes. Okay, I'm happy to discuss this later on. I think, yeah. Thank you for the question, which pointed to an important error in what I was saying. And yeah, thanks for the addition. Okay, but okay. Okay, is that the message clear that I was trying to convey, that you can encode these things? Okay, good. Yeah, okay, good. Okay. Okay, so what are the, okay, so what have we learned apart from the theorem? We learned that you should ask questions. If you don't,
Before,
yes?
before it was the cohomology class, like before you put the generalized metric, it was the cohomology class that was kind of invariant and it didn't change under this choice of splitting.
Yes.
But now it's this antisymmetric kind of B that makes it really, that the full closed thing is the invariant data, right?
I mean, yes.
Good.
Yes. Yeah, it's the, yeah.
It's no longer the homology class, it's really the specific closed
Yes.
form.
Yes, so, okay, so, yes, yeah. So, otherwise, okay, or said in different words, same proof. So, starting from exact, okay, very careful, exact around the algebraic G. What we can do is that, okay, so it's just an alternative way to look at this thing here, is that pick a splitting. This produces a pair G, B, H, with primes, and then the resulting pair of G and H I get by taking this G prime and I take H prime plus DB prime, plus minus depending on what the sign was here. Okay? So one thing that you see here is that whenever I use a different isotropic splitting and I change this triple, the way this triple changes is that from this thing I subtract my B, and to this thing I add or subtract depending on the sign dB. So you see that the combination, like this particular combination is invariant under the change of the isotropic splitting. So another way to arrive at the same result, if you are given an exact cross algebra with a G and you want to get this datum of a two metric and a tree form, is to do this. You just choose any splitting, and then take this thing, and this is the resulting.
Or if you are given the antisymmetric part of G, you get kind of canonical splitting, no? But that's also the one that kills.
Yeah, exactly.
Because prefer to splitting.
Yes. So, so that's another. Okay, this is like remark one. The second remark is that generalized metric. Let's say G induces, G positive induces a preferred splitting. Isotropic splitting of preferred identification. E with this Tm plus T star. And finally, you might have noticed that we have not really used, we haven't, okay, so we actually used the positivity of G in a couple of places, but at the beginning we only used it to show that this thing was a graph of a linear map. So we kind of needed it in a couple of places, but so let's look at the more general statement. So more generally, if I don't want to assume positive definiteness. We have a one-to-one correspondence where here I will take exact Courant algebroids over M with G, with any generalized metric G, metric G, such that the anchor map restricted to V plus is an isomorphism. This map is an isomorphism. So if you go to, this is one-to-one with pairs G H, where G is any metric, so not necessarily Riemannian, not necessarily Riemannian. Metric, and H is a concrete closed strip form. So this is important for right now, for actually the real world applications in like Lorentz geometry. So this new condition, which is, I mean, it's not as nice as G being positive, but this is the condition that ensures that this stuff works. Namely, V plus. If I choose any splitting, V plus will be a graph of something. And and in this way we can get like Lorentz metrics and other things. Okay, so is it roughly clear why I can generalize this?
Can I?
Yes, please.
Good question. I'm sorry if this was said before. So the different choice of splitting for the Courant algebra gives you different rays encoded by this B form. If the two form is closed, then H double prime doesn't change from H prime, right?
Yes, very good.
So these different choices of splitting give you the same pair G H.
Yes, but they changed the B.
They change the B. Okay. I see.
Thank you. Yes, that's a good question. Any other questions? Okay, then if not, then let me tell you two more things about the exact case. So one of them is that, so we have now this kind of mantra that like exact Courant algebra with generalized metric is like a different way of saying that we have such a pair. Now, such a pair important. So, okay, this is just again the remark. So in string theory, so such a pair. So this is a closed, concrete closed reform. This is a metric. Such things are important in string theory. Just say that important. String theory. So last time we were drawing these pictures with surfaces and their embedding and how you can write down an action functional. So in fact, the proper kind of what I was drawing the other day was kind of moral or a kind of local picture. So the kind of the more appropriate global picture is that having such an input. So fix. Okay. So if you fix a surface sigma, so something and some surface, then you want to map it into this. If you are into a manifold which is equivalent to this data, then what you often see in string theory is that people write expressions like this. So they say that if you call this x, then you can write down an action functional for x, whose first part is the area, and the second part is the integral. Let me, for simplicity, make this a closed surface. Okay. Reconsidering my choices. So then what people sometimes say is that you now take a pullback of this 3 form, but you can't really pull, it's 3 form, so if you pull back a 3 form to a 2-dimensional surface at 0, so what you in fact have to do is that you have to pick a auxiliary manifold, let's say, y. So on top of that, assume that y is a 3 manifold whose boundary is x. Okay? So in fact,
I'm sorry, X is embedding or?
no, just any map.
So,
A sigma or x.
Sigma.
oh yeah.
Sorry, sigma. Yeah, thank you. So maybe I should use, since I use the Greek letters, I should use the Greek letters also.
Yes. Upsilon.
Okay. Yeah. Thank you. Or alpha.
No, but I thought you would have to change something. So
Yeah. Yes. That's cool. So this upsilon is a 3 manifold whose boundary. So you can see there's a filling of this thing if you want, and well, you're adding such a thing. So now note that if H was actually dB, then by Stokes, this thing you can use Stokes to localize it to the boundary, so you get precisely the action functional from before. You get an integral over sigma of B. But this is kind of a more global picture where you allow kind of things that are not of this sort. Then of course it's not really true that this depends on X, right? It seems you need. I call it X, but you really need to know how the whole manifold embeds, right? You need to know how Y, which is the filling of this, if you want, like this is like solid torus. So not torus, solid like Riemann surface being filled with some 3-dimensional stuff inside. So I will also need to tell you where the inside gets mapped here, right? So this okay. So it's a bit subtle. I mean, this leads to some interesting considerations. But the important thing is that, okay, so really I should talk about some x tilde, where x tilde is really mapped from y to m, such that x tilde at the boundary of x. So this really depends on this guy. But it turns out that if you talk about the equations of motion of these things, for instance, if you want to derive classical equations of motion, like the extremal is functional, then the only thing that really contributes is what is happening on the boundary. So for many reasons, this really lives only on the boundary. But anyway, let me not go into that in more detail. But let me just say that this is kind of what such a thing is called the Weis-Domino term. It's very common in string theory. Right? This is WZ term. Yeah. So such a thing appears very commonly that you really have a pullback of a curvature into something 1 dimension higher, and you need to make sense of that in some sense. But anyway, this is just to vaguely comment on why this is actually what is important in string theory. So
the interaction with B would be.
There's no B, so B is now H.
I know, but if you turn on a B by doing a gauge transformation, right?
Okay.
By here we are picking a specific M and a specific
Yes,
specific
okay,
H, right? So we can, I guess it pops up somewhere, right? I guess maybe it pops up at the boundary of sigma if sigma has a boundary, because there are many D's, right? in the game.
So,
I mean, just the number version. So if you replace the integral over y with the integral of sigma of b, the easy
yes.
h is db,
Mhm.
and you do a shift by d prime.
Mhm. I guess it needs to be D of A or something, or something. One
Yeah, right. So that okay.
So that
that's
should be
different.
fine.
That's different. Okay.
Okay, yeah,
Okay. Yeah.
yeah.
Okay.
So, good, good, okay. Yeah, it's like this would be like a curvature of a U1 bundle.
Yeah.
That is independent under like local gauge transformations things, because it's only the, if you change the connection, then so this is like U1 curvature. It doesn't change under the gauge transformations. The curvature is invariant under
Yeah, I know, but of which curvature are you talking about?
like
H?
this is like the analog of F.
Yes, but you're talking about H. Yeah, but if you
Yeah,
put the boundary to yeah, whatever.
Yeah, if I would put I don't know. Yeah, I never. Yeah. Okay, that's the thing. Yes, right. I don't know.
It's okay. It's not even clear what my question was. So
No, but it was a good question.
I'm sorry, I have a stupid question.
Yes?
What do you mean by area of X, where X is just some arbitrary number?
Well, what do I mean?
Pull back of the metric and then the area of sigma with respect to that metric.
Well, yes. Well, if it's a Riemannian, if it's positive definite, no, it doesn't matter. Yeah. Sorry, I mean,
It's just pullback
yeah, just pull back, and then you have an induced metric that you use to calculate the volume area
on your Riemannian surface.
on Riemann surface,
Okay.
two-dimensional manifold.
Okay.
Yeah, sorry, that's what I meant. Yeah.
So, okay.
Yeah, so our area of X with respect to area of X. Area of X with respect to the pullback. Area of sigma. Area of sigma. Okay, sorry. Yeah. Okay, I see. Okay, I see the confusion now. Okay, so it's like area of sigma with respect to X pullback of G. Is what I meant. Thank you. I thought you were asking about some singularity.
No, I wasn't sure what you
Yeah, but-
measured actually.
Sorry. Yeah, I didn't mean to think they wrote because it was wrong, but I meant this. Yeah.
Yeah, okay.
Thanks. Good. Any further pointers to some? Yes.
Yes.
What else is wrong?
No, not wrong, but like it's kind of important in physics that if you have to specify x and you ask how does s of x tilde depend on the extension,
Yes.
then you, in good situations, you don't get like any dependence, but it's dependence up to some
Discrete.
quantized things, and then what matters is not action, but the exponential reaction, and that one does not depend on the choice. So this is kind of important. So you said that choice of x doesn't change the equation of motion, but it also doesn't change the exponential reaction, and that's kind of very important. For,
Right.
quantization.
Yes. So what they're saying is that yes. So if I would have a if I don't consider this, but like we did in the other last lecture when we were talking about H fields, if we instead want to quantize the thing and we want to really consider exponential IS, then it turns out that if you choose different, here I should have put tilde, I guess, extension. So if we have two different extensions, so let's say for simplicity, let's say that sigma is 2 sphere. So if I have two different fillings, so I have a map. Okay, so first of all, X is a, suppose that I fix a map to them. And now suppose that I have two different fillings, so I have two different extensions, which are now maps from the three-dimensional pole to them. So if I fix two different ways to extend this thing, then the claim is that if you now compare them, so P3, X1, tilde of h compared to the other one, x1, x2 tilde star of h. Then, because of the nature of the problem, I can now see this as okay. And I want to see them as a map from a three-sphere now. How do I do that?
Yeah, it's like upper house. You know, you imagine V3 as being upper house, sphere,
So-
and lower house here.
Right, so, thank you. So I have, if I will be one-dimensional lower, I will be talking about V2, which is a disk. So I have, imagine that this is one-dimensional lower. So if I have integral from V2,
It's better to call them like disk, like V3, and then it's easier to visualize that it's two disks with kind of rule on equator.
yes, okay, then these maybe.
It's the same, but you know, it's
Yeah, it's not this one case.
Yeah.
Thank you.
But, same.
So if I have two different maps, I have some little bit of a form, and I have two different maps, I can in fact put them into one bigger space. So I can group these two disks into like one two-sphere, and I can say that this is an integral over two-sphere of this map that I obtain if I put these two guys together. There is F1 in here, F2 in here, and I put them together into like one big F. So then I will have a map like this. So here, right?
Yeah, I'm not sure about the dimension. So in the end, you should have three sphere, no? You should have.
No, dimension stays the same. Adds up. 2 and 2 and these two. So here I have the three sphere. Three sphere is like a three ball with an extra.
Yeah.
So yeah, so this thing is really a map from a three sphere
Okay, yeah, so here I'm okay.
of some combination of these x's. I don't know, x tilde tilde, or I don't know, there's no name, x bar. Will make it something. So the moral is that if I choose two different fillings, then because they coincide at the boundary, I can glue them into a larger map, which is now a map from a three sphere. And now if this h had a integer, if this h was an integer cohomology class, then this thing should be multiples of some discrete number. So if I put them in an exponential and I put some like suitable factor, or if I make this a suitable integer cohomology thing, then the exponential is independent of which filling I choose. Because the change, because this thing is discrete, so this is in like z times some multiple a. So if I demand that my h is right, that makes sense, right?
It depends on H.
Yeah. So this is, first of all, okay. But in our case, we don't care about integer cohomology. We take this thing to be any real thing. So this was again just this was a sort of little bit parallel, but since I already started, it's a nice kind of thing, probably. Of course, it's not relevant for the rest of the course, so feel free to forget about it if you want. But I think it's maybe interesting to see this. Although, sorry, I didn't really prepare this part very well. Okay, so this is just to justify why you sometimes care about this, like higher forms. Now, okay, now maybe last. Okay, I think this is a good place to end. So there's two things that I wanted to mention. So one further bullet. So any further questions about this?
What is e to the I? What is s in this thing? Sorry.
It's this s,
Okay, yeah.
and d is exponential,
Yeah, that's how it's good. I
and,
wasn't sure.
and I is square root minus 1.
Standard.
The standard one, the positive one. Anyway, okay, so now one last thing. So this is maybe a different way to look at things. So it's like a local picture. So there is a different way to look at this generalized matrix. So we know that locally, we have locally our exact Courant algebraic is simply Tm plus T star m in the standard bracket, standard current algebra. So the classification is given by cohomologies locally are trivial. So the locally every exact current algebra is simply this thing with no tree form in the bracket. So now if I want to do now sort of like a different look at it from a different angle, I now want to say that this curly G, this generalized metric, it encodes some fields in my physical theory. And to see what these fields locally are, kind of, then what I do instead of talking about what I did before, let me just like fix a local picture, and then any G such that, let me put that assumption that rho V plus is ISO. Okay, it's not terribly essential, but okay. So any such G corresponds to a metric and two form. Okay, so here I'm not doing any of the funny business with identification or anything. I'm just saying like I'm not choosing any splittings. I just fix forever this kind of God-given splitting with this standard current algebra, and I'm just like looking at it. And then we know that this is always a graph of something. So this is kind of like a quick way to see that if you forget about all these kind of global issues, then like locally this generalized metric simply hides the datum of a symmetric and an antisymmetric two form. A symmetric tensor and an antisymmetric two form. Okay? This is a sort of a different way to look at it. Which is kind of less contentful because it's not like global. Anyway, so the reason I put this is that now I want to make the second last example. So if you remember that we discussed how an exact current algebra looks globally, and then we discussed this transitive current algebra as well. So local model of transitive algebra. So what was that thing? So if you remember the E of Tm, any transitive current algebra can be locally seen this for G some Lie algebra with invariant pairing. Okay, and so now suppose G is a generalized metric in this kind of local thing, such that this condition that the anchor map restricted to V plus is an isomorphism. Then how does this look like? So picture. Okay, so I have now a larger space, but I can still draw a picture similar to before. So I have this Tm, and here I put the rest. I put T star m, and plus this Lie algebra, trivial bundle given by multiplying the manifold with the Lie algebra. So now, because I want the rho to be an isomorphism of V plus, that's precisely the condition that in this identification I can see V plus like this. Namely, I can see there's a graph of a map. Graph of map from Tm into the rest. And if I want to, so I want to make another last bullet point. So now, what is an alternative way of describing such a linear map? Well, this is the same thing as saying that I have a tensor. I have a section of T star m tensor the rest. And if I now decode what this is, so what is this thing? So I have a tensor. Tensor probability as a distributive. So it's like I have a T star thing. So this gives me a G on B. Okay, so this is the T star tensor T star bit. But I also have a second bit, which is a one form, which is valued in the Lie algebra. Okay, T star tensor trivial G bundle. So I have precisely some object which is a one form on M valued in the algebra.
So you
Yeah.
T star and that's what with G.
Yes. Yeah. So okay. So I have yeah. This time that's what you get. Sorry.
No, it's okay.
Yeah. Yeah. This time.
That's
Since I have wrote it like this here. Okay, so the moral, I'm sorry if you don't have the space to write it, that the transitive case, got it right there. Transitive case. G really hides in itself a metric, a two-form B, and a connection. This was a local picture, so this is a local picture of a connection. So one form valued in the algebra. So, connection. And this precisely the bosonic field content of what is called type 1 heterotic supergravity. So this is another natural point where this thing touches string theory. So doing it in a more general transitive case, you have the same data as before, but on top of that you have some connections. So there is like some principal G bundles in the game, and there is connections on those, and there is a theory that describes the dynamical of that thing, and that's type 1 or heterotic string theory, and the supergravity is in particular the low energy limit of that. But in any case, there is another connection with string theory. It's the message. Okay, sorry for the slightly more chaotic presentation today. Yeah, question.
Can I ask about the condition of the anchor restricted to plus 3 and then some terms of in the exact case doesn't it always happen?
No, because you can take like, if you assume that it's positive definite, then yes.
Okay.
But if you don't assume that, then no, because you can, for instance, take like this extreme case where you take G to be an identity map. So V plus is the whole E and V minus is 0. That's a generalized metric according to our definition. But it's not, it doesn't satisfy that condition.
Okay.
So yeah, if you assume positive definiteness, then that's for free. If you don't assume, then unfortunately you have to carry this as a baggage.